Section 3.2, Equations of Kinematics in 2 dimensions. Right, so we're going to consider a spaceship. And let's consider a spaceship has this nice thruster that allows it to accelerate in the x direction. So it can start out moving with some initial velocity, and it can apply the thruster that gives it acceleration in the x direction only. And so it's able to go through some displacement and have a larger velocity at the end. Since the acceleration is in the same direction as the velocity, that increases the speed. Awesome. Well, we know how to describe this already. This is what we did for all of chapter 2. We said, hey, we can calculate the final velocity in x based upon the initial velocity in x plus the acceleration in the x direction times the time, right? Similarly, we could solve for the displacement given the initial velocity, the time, and the acceleration. We could solve for the displacement given the initial and final velocity instead of the acceleration. And we could relate the velocities, displacement, and acceleration to each other without time involved. So these equations aren't actually new. The only difference here is I've really emphasized that they're all in the x direction. So my acceleration now has an x subscript to say that this is acceleration purely in the x direction, and my final and initial velocities also have an x subscript to indicate that this is happening purely in the horizontal direction. Okay. So this is pretty straightforward. Now, we can do the same thing if we imagine our spaceship having a thruster underneath it that allows it to accelerate in the vertical direction. So it might be moving vertically, then it applies an acceleration in that same direction, so it starts moving faster in the vertical direction, and we can write those same 4 kinematic equations, again now with y subscripts as opposed to x subscripts. So it's a displacement in y, and the velocities now have this extra y in that subscript, as does the acceleration. Notice time does not have a subscript, because time will be the same no matter which direction you're moving. That's a key for solving problems. All right, so we've seen that we can describe our spacecraft's motion side to side, as well as up and down, using these 8 equations, right? 4 in each direction. Now, we've just described it literally moving in one direction, either up and down or side to side. But it turns out this is enough to also describe it when it's moving 2 directions at once. So the x part of the motion will occur exactly as it would if the y part did not occur at all, and vice versa. In other words, the 2 directions, side to side and up and down, are totally independent of each other. So we can break them down and just consider all the x motion and all the y motion and not have to worry about one changing the other. They're just independent, which is really cool. Let's check out an example of this so you can see it in action. So a moving spacecraft. In the x direction, the spacecraft has an initial velocity component of 22 meters per second and an acceleration of plus 24 meters per second squared. In the y direction, the analogous quantities are 14 meters per second and an acceleration of plus 12 meters per second squared. At time 7 seconds, find a, x, and v sub x, b, y, and v sub y, and c, the final velocity of the spacecraft. All right, so we have this nice picture here that highlights the initial velocities and the x and y components of that initial velocity, as well as the x and y components of the final velocity of the spacecraft, right? The direction of the spacecraft isn't going that it's trying to go 2 different ways at once. The actual direction is that it's a combination of these. So it'd be something like that. Okay, so with this in mind, let's take a look back at our reasoning strategy, slightly modified for 2 directions. So our first step is going to be make a drawing, which we already had one on the last slide. That one's looking good. We want to decide which directions are positive versus negative. It tends to be that to the right is positive and up is positive. 3, write down the values that are given for any of the 5 kinematic variables associated with either direction. That means there's 10 total variables. Verify the information contains values for at least 3 of the kinematic variables. This is step 4. Do this for x and y. then you can select the appropriate equation for x and y. The motion is divided into segments. Remember, the final velocity of one segment is the initial velocity for the next. You got to see this sum last chapter. And then keep in mind, there may be two possible answers to a kinematics problem. This often occurs, or you can see it when you have a square root, and a square root has a plus or minus symbol. And you have to choose which one is going to be appropriate for the given scenario. All right, so with these things in mind, let's go back to our problem. And now notice I have my table as before, but I've written it for the x direction and the y direction. The table's gotten really big, but the reason I encourage this is that then you can just have a methodical approach to solving it, and it can help you remember that you might know some things that you might otherwise forget. So, taking a look at this, I want you to think through what you can fill in on the table. Go ahead and pause the video to do that. Right. So, I'm hoping you did that. Let's take a peek. So, for the acceleration in the x direction is this plus 24. The initial velocity in the x direction, plus 22 meters per second. And then in the y direction, we can do the same. We have plus 12 meters per second squared. Notice the units here really help you to see that this is in fact acceleration versus the 14 meters per second is velocity. It's very easy to mix those up, but the units help you to keep it straight. And then we note that it says at time 7 seconds, and both of them have the same time of 7 seconds. That's because the time is a crossover variable. So if you can solve for the time in one of the tables, you'll have the time in the other. Time stays the same here. That's a really handy thing to keep in mind. And then we note that in part A, it asks us to find the x position and the final velocity in x, and B asks us to find y and the final velocity in y. So we can draw question marks there saying that we are looking for those, as opposed to just leaving it blank and saying we don't really care about them. And then asks us to find the final velocity of the spacecraft. So the final velocity, I will write a question mark for that specifically, because that is something that is bigger than just the individual components of the final velocity Vx and Vy. Right. So at this point, we've done a great job of identifying our variables, and we can note that in both of these tables, we have 3 out of the 5 filled in. That means we can solve for the other 2. So I want you to think about which equations might help us to most directly first solve for position, not knowing the final velocity, and then solve for final velocity, not knowing position. So let's take a look at the equations. So you have them up fresh. And here I've written them out for y and x both. And we can take a peek here. So I'm going to give you a moment to pause and think about that. All right. I'm hoping you did that. Well, if we first want to solve for position without knowing our final velocity, I would recommend this third equation down here. I'll circle it for the x and the y, because both of them we notice we have the same parameters for. So this one does not have final velocity, and it's even set up to solve for our displacement or position, x and y. So that would be our first step. And then our second step is when we want to find the velocity. Find the velocity without necessarily knowing the position, though you could use the result you got from the first part. And if you don't want to use that, then you want to use this top equation, which is a pretty simple equation, so it's a good one to use. So this is going to be the procedure we follow for both the x direction and the y direction. So let's take a gander at that. So in the x direction, we can plug into that equation for x, all of our x quantities, being very careful to pull them directly from the table. This is where writing out in a table makes your math much easier. And you first explicitly writing out the equation in symbol form and then writing everything below it. And when you do that, you should get around 740 meters, where it is rounded to 2 sig figs because our problem specifies 2 sig figs. Right, similarly, you can solve for the final x velocity, and you should find that it is about 190 meters per second, again, when you round to 2 significant figures, based on that limitation. So this is the x direction. We could repeat this for the y direction. For the y direction, we would find that in the final displacement is about 390 meters in the y direction, once again limited by two significant figures. And the final velocity in the y direction is 98 meters per second. Awesome. So at this point, we've filled in our table of all 10 variables, which is awesome. You could argue it's only 9 variables, but I like to just call it 10, keep it simple. The time is valid and important in each of the two tables, so we can count it twice. So are we done now? Not quite, right? Because it asked us to also solve for our final overall velocity. And so for this, we're going to want to know usually the magnitude of the velocity and the direction. So the speed and the direction it's going. And we will then, to do that, we will use our x and y components of the final velocity as shown. So if we know the x component of the velocity is 190 meters per second, that's how fast it's going purely horizontally, and we know how fast it's going in the vertical direction is 98 meters per second, then to get the overall magnitude of the velocity, the speed, we can use our Pythagorean theorem and take the square root of 190 meters per second squared plus 98 meters per second squared, and you will get about 210 meters per second, depending on how you round it. If you use these two numbers exactly, on my calculator, it came out to 213.8, but again, we're restricted to two significant figures, so that's why it's written out as 210 meters per second. Similarly, if we want to know the direction of the final velocity, that's asking about this angle theta, and so that's where this picture comes in handy yet again, and we can say, hey, if we use tangent, that will relate the opposite side, this y component, and the adjacent side, the x component, to this angle theta. So inverse tangent of the opposite, v sub y, all over the adjacent, v sub x. And when you plug in those numbers, you get an angle of 27 degrees. So that highlights how we can break the problem down into purely x direction, purely y direction, with time being the only crossover variable between them. And then at the very end, we can pull them together and see how having a velocity in the y direction as well as the x direction means your overall velocity will be larger. 210 is larger than either the individual components. And you can get the exact direction that's neither purely in the x or purely in the y direction. So this introduces the equations of kinematics in 2 dimensions.